The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. Welcome to today's webinar, Relay Input Sources. My name is Tracy Noble with ABB Power Systems, and I will be moderating today's webinar. Before we get started, I wanted to go over a few housekeeping items with you. All participant audio will be muted during today's event. If you would like to ask a question, please use the question box on the GoToWebinar control panel on the right side of your screen. We will answer as many questions as possible at the end of the event. Please ask your questions during the presentation so they will be available when we go to them at the end. Today's webinar is being recorded, and a link to the recording will be emailed to you following today's event. Feel free to forward the link on to people you know would benefit from the presentation. This webinar series is brought to you by the RELiON product family, Advanced Protection and Control from ABB. And now a word from our legal department. ABB is pleased to provide you with the technical information regarding protective relays. The material included is not intended to be a complete representation of all potential problems and solutions related to this topic. The content is generic and may not be applicable for circumstances or equipment at any specific facility. By participating in ABB's web-based protective relay school, you agree that ABB is providing this information to you on an informational basis only and makes no warranties, representations, or guarantees as to the efficacy or commercial utility of the information for any specific application or purpose, and ABB is not responsible for any action taken in reliance on the information contained herein. ABB consultants and service representatives are available to study specific operations and make recommendations on improving safety, efficiency, and profitability. Contact an ABB sales representative for further information. And again, today's session is Relay Input Sources with Roger Heading. Roger graduated from Marquette University and joined Westinghouse Electric Corp. After receiving a master's degree in electrical engineering from the University of Pittsburgh, Roger became a district engineer and eventually moved to Milwaukee, where he currently resides. As a relay development consultant, he guides the development of relay products for the North American market. Roger is an IEEE senior member and vice chair of the IEEE Power Systems Relay Committee. Roger has authored or co-authored many papers in power systems protection. And it is my great pleasure to introduce Roger Heading. Take it away, Roger.
Thank you, Tracy. And thank you, everybody, for tuning into our broadcast of this seminar on relay input sources. If any of you were available or tuned into our broadcast where we started this webinar series earlier this year, our first seminar was called Introduction to Protective Relay. And in that introductory session, Elmo Price, who I believe was the presenter, made a statement that says relays are not an island, and so a relay cannot operate by itself. It's part of a scheme, a team. The team being made up of the relay input sources, which would be the current transformers and voltage transformers feeding into the relay, providing information about what's going on, and then of course the circuit breaker output that operates when the relay says to take that operation. So this actual seminar should really have been in a sequence. It should have been right after that seminar on Introduction to Protective Relaying. But because of other issues and vacation and stuff, you're not going to receive it till today. So you just have to go back and look at your old notes and stuff to see where this fits in. But for today's seminar, I'm so excited to present this to you, and we're going to talk about what are instrument transformers. What are these devices that take these high voltage currents and voltages and transform them to usable voltages that our relays could use. There's some application issues associated with voltage transformers and CCVTs. We'll talk about what those issues are, and hopefully you'll get an idea about how to apply these. Next, we'll talk about current transformers and a lot of issues dealing with current transformers, and you should learn a little bit about them. And then we'll conclude with some information on non-conventional sources. There are other things other than current transformers and voltage transformers out that do the same job that that have been on the market now, Rogowski coils and optical current and voltage sensors and resistance boxes and stuff. So we'll do a little bit of talking about that also toward the end. So that's our schedule about how this is going to happen. So let's get right into it, because we have lots of things to cover in a short period of time. Actually, Tracy doesn't think I'll be able to do it, but we'll see. First thing is talking about instrument transformers. We have the two main types of transformers. Is one device that transforms a current from a high current value to a lower current value input to the relay, and the second is a voltage device that transforms the voltage from a high voltage to a lower voltage input to the device. You can see both of the current transformer is and the voltage transformer are basically the same thing, and not the same thing, but use the same principle. They both have a magnetic core, iron core, and that iron core has in the situation of a current transformer has a single turn primary and multiple turns on the secondary in order to get that current down. In the case of a voltage transformer, we have a multiple turns in our primary and lesser turns on the secondary to reduce the voltage down to a usable voltage level into the relay. A thing I want to show you whoops, go back one, to show you specifically is these dots that you see both on the current transformer and the voltage transformer. These are called polarity marks, and those are extremely, extremely important when you're using these in conjunction with relays, is to pay close attention to these polarity marks, because that tells you the exact direction of a current flow, and it tells you the polarity on the voltage transformer. So by convention, as far as these dots are concerned, the current into the dot on the primary of the current transformer is at that same instant in time, there'll be a current going out of the dot on the secondary of the current transformer. And on the voltage transformer, a plus polarity on the voltage transformer primary will be a plus polarity on the voltage transformer secondary where the dots are concerned. So that's, and then on the right you can see pictures of what these two devices look like. Obviously this is a low voltage instrument transformer in both cases. So what we use these things for? We have to accurately produce we can't use the primary voltage and primary current because it's too high, and we have to accurately produce a replica of that primary voltage and current to a lower value so they can feed into our meters and relays. This device provides isolation between the primary and the secondary, so we don't get all the transients coming into any high voltage transient that won't necessarily, on the primary won't necessarily reflect it on the secondary. And we also provide some secondary circuit isolation to the relay also because of that. The voltage transformers are designed for minimum voltage magnitude and minimum phase angle error, where the CTs are designed to minimize the current designed to minimize the current magnitude and phase angle error. In both cases, the phase angle error is very important, obviously, to both these devices. Looking at the connections for these devices, we see a current transformer is connected in series with the line, wherein the voltage transformer is connected in parallel with the line. So we're measuring a line-to-ground voltage or a phase-to-phase voltage with the voltage transformer, and the current, of course, is measuring a through current on the line for the current transformer that are being fed into either meters or relays or whatever. The two types of things we're going to talk about is voltage transformation and current transformation. For voltage transformation, we'll talk about the electromagnetic historical voltage transformer, the coupled capacitor voltage transformer that's used at higher voltage levels, and the optical voltage transformer used the EOVT type principle, Optical effect. In the current transformer, we'll talk about the electromagnetic current transformer, the optical current transformer, and the Rogowski coil. Starting with voltage transformers then, A voltage transformer is an inductive device where we have voltage on the primary. It gets transformed by the magnetics of the iron core to the secondary, and the secondary is where we measure it going into the relay. They don't differ materially from a large power transformer, except it's much smaller power rating, and we designed this to minimize the ratio error and to minimize the losses and the phase angle error, because we want to get the secondary voltage to be as close to in phase and representing a magnitude difference between to the primary. So it's important to keep that phase angle error down. The application of voltage transformers, though, is limited to values typically less than 69 or possibly 138 kV. Typically 69 kV and below, you tend to use a magnetic voltage transformer, and above 69 kV, because of economics, we tend to use a coupled capacitor voltage transformer instead. The equivalent circuit for a voltage transformer is just that you have an ideal turn, and the one would be the ideal transformer. Then we have a secondary, an impedance on the secondary, which is the high side impedance that's transformed by the turns ratio. We have a magnetizing impedance branch with RM and XM, and then we have a secondary impedance and a secondary and lead impedance represented by ZL, and then our output across EF, of course, we have a burden connected to that. Because the magnetizing branch is such a high value of RM and RX and XM, we can neglect that, and the equivalent circuit we see in B is what's then derived. By looking at the relationships, we input a voltage CD, which is VAB divided by the turns ratio, so that's what VCD is, and then we have some losses within the device too. We have a loss due to the IL flowing through the ZH over N squared plus ZL, and we have a resistive and a reactive loss because of that, and that's what you see on this vector here. So the actual output we have across the burden is this VEF value, and VEF value is just transforming the turns ratio, but then there's this phase angle error that you see across here too that we try to minimize as much as possible. When you get up to higher voltages, though, it's been accustomed since the late 1960s to use a CCVT. A CCVT is a coupled capacitor voltage transformer, or if you don't have carrier accessories on it, it's just called the capacitor voltage transformer. It's much less expensive at higher voltages than the electromagnetic voltage transformer, and it's just based on capacitive coupling across the capacitor stack. And but there's some things we need to look at a little more closely with the CCVT that we'll look at, because we have a series of capacitors and inductors, as you'll see. We get into some transit issues that we need to be concerned about. So if you look at the inside of a coupled capacitor voltage transformer, this is what you'll see. You'll see a large stack inside a bushing, and the stack is tapped at some level of around anywhere from 5 kV up to 24 kV, and that stack, that capacitor stack, that tap is then fed through a transformer, and that transformer transformed that 5 kV voltage or 24 kV voltage down to 120 volt level that we can feed into our relays. And there's expansion parts in here for oil expansion because this whole stack is immersed in oil typically, and so there's expansion so that we can move it during high temperature conditions and stuff, and other parts that you can see on there too. Looking at the simplified schematic of the CCVT, we see the capacitor stack, which is C1 and C2, that's from line to ground. And then we have a tap at C2 to ground, and in that tap we have a inductor, and then the transformer, secondary transformer, and then the output that you see here. There's an inductor located in this circuit, and the inductor's purpose is because we want to get this voltage to be as close as it can to the primary voltage phase angle wise. So we put an inductor in here to try to minimize minimize all the capacitance in the circuit, so that it cancels out the capacitance. So we have like so it looks like a resistor burden to the world, so it looks like it's in phase. In order to minimize some effects of this capacitor-inductor combination, we have ferroresonance suppression on the secondary, and there's two types of that. One is a passive type ferroresonance suppression, that's a inductor and resistor in parallel. Then there's an active type ferroresonance suppression that has a capacitor, an inductor, and a resistor in the circuit. So if we talk about active ferroresonance suppression, if you hear that terminology, that means there's a capacitor involved in the ferroresonance suppression, where in the passive type it's just the reactor and resistor. Looking at the frequency response of the two, you can see that the dotted line you see is the passive type of ferroresonance suppression, and the connected line is the active type ferroresonance suppression. There's certain things that you can control on a CCVT design. One is, and these will perfect the performance of the CCVT. One is the magnitude of the tap and the stack capacitance, C1 and C2. Next is the turn ratio of intermediate transformer, or easier said, the voltage at the tap, and then it's have ferroresonance suppression that we use in the circuit. You as a user can control the magnitude and the power factor of the burden that you apply to the CCVT, which will have some effects also, as you'll see later. And you have some control over the magnitude of the stack capacitance, because you can buy different types of CCVTs with different ratings of capacitance for your applications also. But you can't control anything about the voltage transients from that are controlled by the point of wave where it's switched and the magnitude of the voltage difference. So this is the kind of burden designation that you see for testing a CCVT that we see here. We have a ZT burden and a ZCT burden, where the ZZT burden is 400 volt amps and the ZT burden is 200 volt amps, and you can see how this equates to the resistance and reactance. This will come into play momentarily when we talk about the response. I talked before that depending on the capacitor tap voltage that you choose and the amount of capacitance that you have in the CCVT depends on the amount of transient that will be developed. By transient, we mean the amount, if I have a voltage, a CCVT, and I suddenly drop the primary voltage to 0, the secondary voltage ideally should go right to 0 also. But in some cases, that secondary voltage, well, in most cases, because the LC combinations inside the device will get a bring down effect, so it won't go to 0 directly. So in this particular graph, this is for a PCA9 CCVT of Westhouse, which is designed from the late 1970s or so, and you can see that for a 5 kV tap, this is a very low tap with a very small step capacitance of 0.0058 microfarads, that we get this large transient. This is percent residual voltage after we turn off set the voltage to 0, so we get just about a 10% overshoot on voltage when we remove it. Whereas if we have a unit with a higher tap voltage of 8.1 kV and a higher capacitance, then we'll get a much lower residual voltage. So it's down to around 4% or so. So you can, and if we go to extremely low to a higher capacitance yet of 0.0135 microfarads and 8.1 kV tap, you can see we can get that residual voltage down to around 2% or so. Ideally, the lower voltage you get, obviously, the better off you'll be for relay protection applications for voltage. If you look at the response using different types of designs for different types of fluorescence suppression, the PCA7 that you see down here has strictly a inactive fluorescence suppression. That's why you don't see any ringing in it at all. So it has a overshoot of around 7%. When you get into, but it lasts much longer, and it lasts upwards of 15 milliseconds before it dies out. Whereas the PCMX type design, which is more used for metering, it has a active fluorescence suppression, but it has a much higher response, and it goes up to 16% over voltage temporarily before it brings down, but it brings down much faster. And then we look at the burden that we can have. As we said before, the ZZT burden was a 400 volt amp burden. The ZT burden was 200 volt amp. And you can see, but at the higher the burden you put on these devices, the more residual voltage you'll get when you turn off the voltage also. So here we have 15% for the ZZT burden, and if you put a quarter of the ZT burden on, which would be only 50 volt amps, it goes down to a value like 10% or so over. So you can see as we lower the burden on the CCVT, we get a better transient response also. I talked before about these older type designs. This is for the latest type designs that are being made right now. These are the kinds of that you see for the capacitance that you see is about 0.09 microfarads or 0.14 microfarads, and the transient overreach on these is less than 6%, or even less than 5%. Or if you go to a higher taps of the 24 kV divided by the square root of 3 tap, then you'll see a transient overreach of only 5% in those also. So these are the modern equivalent that we have nowadays that we're supplying into the industry for CCVT designs. So so the magnitude of, if the magnitude of the stack is high, then we'll get a small transient. If it's low, you get a larger transient. If the turns ratio, intermediate transformer, or the tap voltage is high, we get a smaller transient, and if it's low, we get a, so you can see for yourself that depending on how you choose the CCVT, you can get a higher transient response. And what does this transient response do to you? It affects the relays is the fact that it will affect the zone 1 reach on a relay. On zone 2 and zone 3 relays where you have a time delay associated with them, the time delay is such that the time delay will time out before the transient will die out before the time delay occurs at all. So you'll be able to ride through that time delay before the relay has to operate. But if you get into operations for zone 1 where there's no intentional delay at all, then you need to worry about this error. And so, and the relay, because the value of V of I is smaller, the relay tends to overreach a bit when this happens. So Franklin and Horton wrote a paper some years back called Determining Distance Relay Zone 1 Reach Settings to Prevent CCVT Overreach. And they used some of the first generation microprocessor relays when they did the study. And they found out the worst case condition for this transient overreach was for a phase-to-phase fault and with the SIR of 5 or so. So what you see in this graph is this blue line that you see is the ideal CCVT and ideal voltage transformer. That this is for a fault. This is where it's supposed to. It's a close and external fault. So, but the relay it was right outside its boundary area. So the response should be that we don't operate the relay, but it's right outside the boundary. What you see in the red is the actual trajectory of the impedance plot for the CCVT that was used in this case. And you can see that it intersects the modal circle and stays in the modal circle for quite some time before eventually coming back out again. So, and as you all know, that whenever a impedance plot intersects the modal circle, it will be the operate time. So if this would have misoperated for this particular condition. So they took it one step further, and they said that how much do I have to decrease the zone 1 reach on the relay for this kind of condition? And again, for these first vintage microprocessor relays and the this vintage PCA7 CCVTs, and they found out that this curve shows for several different loading conditions, anywhere from 1,500 megawatt out of the relay to 30 megawatts out of the relay to 1,500 megawatts into the relay. And they found the worst case was for huge flows flowing toward the relay. And they found out that for like an SIR of 5, that you'd have to change the reach to the relay, you'd have to reduce the reach to the relay by about 65% so it doesn't overreach the power bus. And so if you had older vintage microprocessor relays, this is what you had to do. But in modern microprocessor relays, we have methods of dealing with that. But in the older ones, if you put a time delay on the zone 1 element so that it lasts, that time delay was longer than the CCVT transient, of course, you wouldn't have to draw back the reach of the relay. Or if you use a narrow band DFT phase comparators, which is done now in microprocessor relays, we can get around that. But when you add narrow band DFT phase comparator filters, that kind of reduces a little bit the operating speed of the relay anytime you go through any filtering, so the speed of the relay is slightly decreased because of that. Electromechanical relays, because of the masses they were involved, they weren't susceptible to this either. There were torque-based algorithms within relays, also because the emulated electromechanical relays weren't infected by this. So relays now using low-pass filters that mitigate the CCVT transient, but they're a little bit slower because of that, and they may, depending on how long the transient is, they may reduce the operating speed of the relay up to 10 milliseconds. So to counteract that measure, some relay manufacturers actually put in a setting in the relay that you can either turn on or turn off this function. If you happen to be using a condenser wire around VTs, you don't need to use that, obviously. All right, now we're going to do a bit on current transformers. Current transformers are, as we said before, you can either buy, depending on what kind of word the use is going to be, if you're using a dead tank breaker, which lots of breakers are in the industry, then it's a bushing type CT on the inside the live tank breaker, dead tank breaker. If it's a live tank breaker, there's no room for CTs on it, and you have to use an external CT, and usually those are freestanding type CTs with multiple cores on them. Or in switchgear, lots of times you'll see the CTs will be in the bus with the cables. The equivalent circuit for the CT looks quite a bit similar to what it looked like for a VT, in that we have, again, an ideal transformer with the high side impedance reflected secondary, and it turns the magnetizing branch, again as usual, and a secondary impedance, and then a burden on the secondary. But in this case, because we need to have that XM magnetizing branch in the circuit, we can't exclude it like we did in the case of the voltage transformer. And the amount of current that we draw in the secondary of the magnetizing branch plays a big factor in the accuracy of the current transformer. By definition, the C designation for current transformers says that the amount of magnetizing current that we draw, this IE that you see in the picture, can't be greater than 10% of the rated current going through the current transformer up to 20 times rated current. So that means that if I have a 5 amp current transformer and I put in a 20 times rated current, that would be 100 amp secondary. And for 100 amp secondary, I can't have more than 10 amps flowing through IE. And we'll show that a little bit more, a little later when we get into some calculations. So because we have this current flowing through this magnetizing branch, if all of a sudden and we have another amount of current that's flowing, it's this much higher current, much higher value than magnetizing branches than our burden. So we have an equal split between, we have a split between the current flowing through the magnetizing branch, this exciting current, and the current that's flowing out to serve our load, our burden. If all of a sudden we open up our burden and we force all the current to go through the magnetizing branch, now where we had a very small burden of 1 ohm or 2 ohms or 3 ohms or so across the burden, now we have all of our current trying to go through this magnetizing branch, which is in the kilo ohms. So all of a sudden, when it happens, we get a very, very large voltage developed across there, and that's what you see. That's why they talk about CT flashovers and getting these really large over voltages when you open circuit the CT. So the flux in the core, instead of being difference of the primary and secondary amperature, now tries to flow all the way through the magnetizing branch. This causes a really large increase in flux and a very high voltage on the secondary terminals, and you cause some spiking. So we need to prevent that from happening, obviously. There's 3 ways that we could use to evaluate the performance from a steady state value of the steady state performance of the current transformer. One is the formula method, one is the excitation current method, and the third is that's the accuracy. There's a question here. A question came up about potential transformers. I never got to visit because this was so small here. But someone asked a question: can the PT be used for both relaying and supplying power as long as the stays below the kVA rating, or must it be used for one or the other but not both? Actually, there were some PTs be used that were called power PTs that were used for supplying both police metering and power to stations for a while. But I guess, but typically you tend to separate those two and just use a separate auxiliary power source for the power for the station and use a separate electrical transformer. But some have been used for both. What are the physical effects on the CT at 20 times rating is exceeded? Does the core get damaged? No, the core doesn't get damaged, but you start drawing a lot more exciting current. So 2 things happen. One is that the windings themselves will start to overheat when you get more than 20 times rated current through the secondary. And second, you'll start getting more and more current starts going into, you'll start saturating the current transformer, and you're actually, because of a large primary current, and you'll wind up, but it typically won't damage it unless the current gets extremely high. Hope that answers both those questions for you. Okay. Next, as I was saying, we could look at this, evaluating the CT steady state performance. And one way to do this is using a formula method. Step 1 is determine the voltage required to be supplied by the CT. This is the voltage required to drive your instrument that you have in the secondary. The secondary voltage is equal to the IL, which is the secondary current that you have in a current transformer, times the secondary impedance load of the primary and the secondary, which is ZL, plus the lead the lead impedance plus the relay impedance. Add those three together, multiply times IL, and that'll give you the amount of voltage you're getting across the secondary of the voltage transformer. Then, after we know what voltage we're going to have, we can determine what the by the turns ratio and the cross-sectional ion core CT, we can then determine what size CT we need to have in order to perform that, get that information. And then after we determine the V required that we need to have, we could use this equation to determine if our CT will meet those needs by using the VS required, the secondary voltage required that we calculated, and then with the physical dimensions and stuff for the CT, we could determine what the V required is going to be, which is the flux required, and that typically is less than 100,000 lines per square inch. A more common way to do this is to use a steady-state performance excitation current method. And this is a typical excitation curve for a multi-ratio CT that has the ratios anywhere from 600 to 5 down to 250 to 5, or 50 to 5 up to 600 to 5. You can see the ratios, and you can see the secondary resistance of the secondary coil here, also secondary turns here also. And we can use this information. This is a plot they normally give you of the secondary exciting voltage versus the secondary exciting current. So we can use this plot and plot another plot of the secondary current versus a primary current on the curve, and that's what we're going to do right now. So first you assume a certain secondary current that you want. You determine the secondary voltage from that secondary current, and from that you can determine by using the curve with this secondary voltage what the primary exciting current is going to be. From that primary exciting current, you can add that to the secondary current that you want, and that will tell you what the primary current has to be. So using that we can then plot a curve for various points. We can plot a curve for a given turns ratio of the secondary current versus the primary current. As we talked about a little earlier, the C classification, which is how most CTs are rated in this country, at least for ANSI is concerned, are either carry a C-rated or a T-rated. A C-rated means that leakage flux is negligible, which means you're not going to have much current flowing in the leakage path. The CT ratio error can be calculated, and the CT excitation characteristics can be used directly to determine the performance, and that's exactly what we did in that previous method. T classification means that you can only determine the leakage impedance by measurement. You can't do it by test. You have to do it by test. You can't do it by calculations. So the classification, the C classification, is based on a error of not less than 10% when the current is 1 to 20 times nominal current flowing through the current transformer. Somebody asking the question I don't see here. The classification defines how much voltage the CT can supply to the output without the CT core going into saturation. And the standard ratings are 50, 100, 200, 400, and 800 for the classifications. So if you look at these on a curve, you'll see here that for the standard ANSI classifications, we have like a C100 class, a 200 class, 400 class, and 800 class. And all these values, this C100, 200, 400, and 800 is actually the CT secondary volts that you get on the secondary when you put 120 times rated current on the flowing through the relay. Excuse me, flowing through the CT, which means if I have a 5 amps nominal secondary CT and 20 times that would be 100 amps. So we look here at the secondary current of 100 amps, and we read up on our curve, and we see C100 is exactly 100 secondary volts at the terminal. C200 has 200 secondary volts at the terminal. C400 will have 400 secondary volts at the terminal. And C800 will have 800 secondary volts at the terminal. That's how these are rated. So, and then these are the amount of burden that you can have on the secondary and still obtain that kind of rating. So for example, a C400 class CT will have an error of less than 10% exciting current for a 400 volt max across the secondary with 100 amps or 20 times 5 amps rated current on this, through a 4 ohm burden. So, which means that if we have 100 volts on the secondary and we have 4 ohms here, then we'll have not more than 10 amps of exciting current flowing when we have 100 amps flowing through ZL. So a question would come up: if I had a maximum secondary current of 50 amps, can the CT be loaded to 8 ohms burden? Because 8 ohms times 50 amps is equal to 400 volt amps. Well, the answer to that is no, because as soon as you say 400 volt amps, 400 volts, that means my exciting current is going to be 10 amps. And if I have if my IB and my current flowing through my IB branch is only 50 amps, and I have 10 amps exciting current, that means I'm going to have a 20% inaccuracy on this. So it would be would not be, you could not use that 8 ohm burden on that, or 4 ohm burden on that. Okay, I hope there's no questions about that at all. Next, we'll go through CT transients. Faults in a power system are sudden and are often accompanied by transients. And as we said before, we want these current transformers to accurately reproduce what's going on in the primary system with very little phase angle error or magnitude error. But these transients could be such that even though we rated our relay, our CT properly from a static rating, it won't be good from a dynamic rating point of view, and that's what we'll talk about right now. The transients only last a few power system cycles, but they definitely can affect the performance of fast-acting breakers and protective relays. One thing nice about, about a current transformer is that if you throw enough current through a current transformer, the amount of current that goes in the exciting winding, which will eventually, as you put more and more current through the exciting winding, the current transformer will eventually saturate. The nice thing about, the one inherent nice thing about saturation is that it doesn't happen immediately, and it takes a while for the flux to build up to the point where the CT saturates. So we have this factor known as a time to saturation that we can use on our power system studies to determine if the CT will actually perform properly for us in a given situation. So the time to saturation that we have is made up of several factors. One is the maximum residual flux that we have in the current transformer, the level of fault current that we're applying to the current transformer, the system time constants, and the parameters of the CT and the burden. So the residual flux that we're going to have is depending on the type of core and the type of and what's happening on the current transformer prior to the last time it was interrupted. The current was interrupted. which means that if I open up a breaker, as soon as I open up the breaker, depending on what point of the waveform that the current is at that particular point, then that residual current will be left as a residual flux in our current transformer. The flux in turn depends on the magnitude of the primary current, or when we're opening up the breaker up, the amplitude and time constant of any offset transients, and the impedance of the secondary source. Residual flux with no air gap, which means I have no air gap in the core itself on the current transformer, will never be greater than 90% of the saturation flux density. The saturation flux density is the point on this Vs on this curve where the current transformer goes from a magnetizer reactance to an air core reactance, and that's typically about anywhere from 1.15 to 1.3 per unit per unit. And our residual flux won't be greater than 90% of that. The residual flux with the air gap is usually only around a value of 10% of the saturation flux density. So often that's why you say air gap current transformers have a longer time to saturation. To avoid saturation during the faults with unfavorable residual flux requires about 3 times the core area that you would normally need for steady state conditions. So we typically don't design current transformers for that type of a core area, so it'd be way too expensive. So we have to just learn how to deal with it. Residual flux could also develop when you test a current transformer, so when you're using a battery to test it, you put a DC on the core and it develops a flux, and that flux stays there. So oftentimes you have to use some method of degauss that CT to get that flux back down again to a zero level. Then again, that only lasts until the CT is energized again. The next time the breaker opens, it's going to have a residual flux in it again. So residual flux is something we already have to just live with in the current transformer. There's also a DC component in the CT too, because of what happens on the system. Whenever we have a system voltage and current in a normal system, then we have a fault occurs. All of a sudden, we have to put a mimic DC level into the system in order to accommodate that change, and we have all of a sudden now we have a DC trap component that's in our current transformer, and that trap component will have to die out eventually, and so we get the time to saturation is even faster. It's different if you have a fully offset current, fully offset fault, or a no offset. With no offset, our flux will change just as it should, and we don't have to have any DC offset in order to fulfill the flux requirements. But when we have a fully offset wave, then we have to build up a flux instantaneously in order to compensate for the current, and we get this DC component. So the saturation of a CT may occur because of the offset fault currents and DC component, or residual flux in the core. So we just have to learn how to deal with the microprocessor relays. What happens when a CT saturates is that the amount of current we have in the secondary decreases as soon as we draw more and more exciting current, and less current goes into the secondary, or i.e. in the relay. So in this particular example, we have you can see that the solid line is the line that is the current that should exist without any saturation, and the dotted line is a line that exists with saturation. So you can see that for the first half cycle, we have no saturation, and then we get to the second cycle, and at this point now, we have a lot of this DC flux in our current transformer, and the CT saturates, and it drives our secondary current down to 0, and it stays that way until we start putting a negative half cycle current through it, so we unsaturated again, and then we unsaturate for a little bit longer, and then eventually we get our core saturated again, and then we go down to 0 current again. So there's two things I want to point out with this diagram. First, we don't saturate the CT right away. It takes a time, i.e. this time to saturation before it finally saturates. And here we have it's work a cycle and a quarter before it saturates. And then this CT saturation only lasts for so long, and eventually it will come back out of saturation again as you get further and further down as time elapses. So this time to saturation is important, and that's what you need to calculate for my dynamic performance for the CT when you're putting these in various applications. Here's a picture of the CT saturation here. That you can see this little blip here is where the CT had saturated for a little bit on the phase A current. What do we do now with modern microprocessor relays? We can use the information in the relay to determine if the CT is saturated or CT is open circuited. And the next couple of slides will just show you how some microprocessor relays can handle this, just so you get an idea about how this can be done. This happens to be a bus differential relay that talks about how it handles internal fault, external fault, and open CT saturation, open CT circuit conditions. So here's the condition. The first thing we're going to do is we're going to show you what the relay sees. This is the input current to the relay. This is a pre-fault condition where you see the current that's less than 2 amps here. And then after the 41st sample, we get an internal fault. And the internal fault goes, current gets much, much higher, and we see it goes up to 14 per unit or so, 14 amps or so on this, and then it follows that for several cycles. This is what's called the IN current. When we have this internal fault, our pre-fault conditions are input current or output current through our differential circuit is the same, so that you see that current, and this current that you see in pink now is the output current, and the output current matches the input current exactly before the fault. At the point of the fault, the input current goes up, but the output current, because the fault is internal, goes down to 0. So we have this difference between the output current and the input current in this differential analyzer. And whenever the output current and input current exceed the ID value, the differential operate level, then we issue a trip in the relay. So this is the difference between the two, and when we get up to a certain level here, we issue a trip in the relay, and the relay operates. So we have these sample values of yellow arrows show the sample value of the integral of the sample value of the RMS value for the input currents, and the light blue values show the RMS value for the output current. And when they exceed the differential value, the difference between these two, then the relay trips. For an external fault, we have the same kind of thing for the input. We have pre-fault conditions and the fault conditions for the input current. But now what happens if our CT saturates? If our CT saturate, our output current starts out as the same as the input, and then we get to the point where the CT saturates, and this relay time the CT is saturating before we get to even half cycle point or the quarter cycle point, and when it saturates, the current goes to 0. So again, we have our RMS current for the input, which is still steadily increasing, and our RMS current for the output is going along the same lines as the input, even while a fault occurs, and you can see these two are both together while the fault is occurring, then at a certain point it drops down to a minimum value again while the input curve keeps going up. And the relay just says, we just had we have the two currents are the same, and they both start rising up like it's an internal, like there's a fault. Then all of a sudden one current goes down and the other one keeps going up. We're going to see it because these two are the same for a while. This was an external fault, so it makes the decision right here that this is an external fault, and with CT saturation, and the relay refrains from operating. For an open circuit CT, this is a long open circuit CT is after the relay has been in service for some time and the CTs are put out normal currents. All of a sudden, when CT open circuits, and this is what happens. So we have a circuit that we have all the input currents are high, and the CT is working as it should. CT is working as it should. Then all of a sudden, for several cycles, the relay, all this input output is the same. Then all of a sudden, the output drops down to this lower value that you see in pink again. We do the RMS calculation again for the yellow for the RMS value of the wave, and staying at a constant level. Then we see the same thing for the output currents that are staying at the same level. Because all of a sudden our output current goes down and goes to another level. And the relay says that because these two are at this high level together, and the output starts dropping down into a lower level, it's a lower level, it's saying this change in current where it drops down to a lower level must mean there's an open circuit CT, and it alarms for that. That's how we do this open circuit CT detection in this relay. So that's pretty interesting. I mean, so that's how we can get around problems with CTs and modern microprocessor relays. Next thing I want to talk about briefly is stray flux in the effect on CT performance. Typically, when we think of a current transformer, we think of the primary and the secondary on the current transformer being infinitely long, exactly in the middle of the core of the current transformer, and there's no other carry members anywhere close to this. So all the flux generated is going to be the flux generated by this one conductor on our core. But in reality, in practice, this could be different. If I have a current transformer that and I have other conductors close to this, or I have an abrupt bend in the CT primary conductor, or another high current conductor right close to the CT that's external to the CT, I can cause some problems with the amount of actual flux that's being generated, that's flowing in a core of our current transformer. Here's a case where we have an external source of stray flux, and you can see this external source of stray flux generates two separate fluxes in the core of our nearby current transformer, one flowing in one direction and one flowing in the other direction. That on one side it's in phase with the core, the other side is exactly out of phase with the flux from the primary conductor. And it causes big problems in what kind of output current you're going to get from the current transformer. Here's a test that was done where we took a primary conductor and put it adjacent to a current transformer. And we ran a high current 6.5 kiloamps through this external conductor and looked at the secondary of the current transformer and the current to see what kind of current we're going to get. The distance between the primary conductor and the center point of the current transformer is around 6 centimeters. Its primary conductor. So this is what we found. We found that we injected this kind of a current in the primary conductor, and that's what you see on this first trace here. And then the current we got on our conductor, on our current transformer, was this large spike and then another shorter spike, and then it dies out to the shorter spikes along the way. So we get a huge spike out of that. Even though that current transformer was some distance away from our primary conductor, we're getting that much influence on it. This is where this comes into play. Is that here's a case of an a phase shifting transformer, 450 MVA phase shifting transformer, 138 kV with a plus or minus 58-degree phase shift. There's 6 buried CTs in here in this kind of a design. We have buried CTs at each of these different points that you see here around the core, inside the tank, and we wound up getting some spurious tripping on the differential protection during the phase shifting transformer energization. Once every 10 times this would spuriously trip. Location-wise, you can see that we have these are the 2 current transformers, and you can see the conductors are right next to each other, and these current transformers inside the tank, very close proximity to each other, where the leads are coming down through here and in through the current transformer. So this blue line is showing you in a test that was run. This is the kind of current that we should be seeing in the current transformer in the dotted blue line. What we actually got out of the current transformer was what you see in red instead, these jagged lines that you see here. And the problem was that resulted in a differential current that you see in this black, and this differential current was way more than enough to trip the differential relay. So the differential relay was tripping on energization of this device. Where does this happen? If you have CTs within low voltage or middle voltage switchgear, if you have CTs within high voltage gas insulated substations, at CTs at the generator terminals, and CTs at the bus ducts. Any of these are CTs buried in power transformers or phase shifting transformers or shunt reactor tanks, where they're in close proximity to other high current carrying members. Any place here you can get this problem to occur. And there's different mitigation ways you can mitigate this. One, by increasing the relay pickup settings on the relays. One, to put in some intentional delay so you get over the part where these spikes are occurring. Another way is to use differential protection principle, which you don't use buried CTs. And another way would be to change the CT location if possible. But if you have buried CTs inside of a tank of a transformer, that can't very well be the case. Another thing to do is use a separate kind of a CT that has a flux equalizing winding on it that actually cancels out that flux that you're getting from external sources. So that's just something I thought I would bring to your attention. Next thing is I want to talk about now is new sensor technology. Some non-traditional ways to apply non-traditional type instrument transformers. Traditional transformers, PTs and CTs, when we lived within the age of electromechanical relays, we required high currents and voltages inputs to these electromechanical relays for them to operate. The relays wouldn't operate on small power levels at all. They had to be large currents. Today's modern digital relays could use a process bus which don't require high power sensors at all. We could use matter of fact, most all digital relays have a A to D converter in it. Any current coming into the modern microprocessor relays now goes through another transformer that transforms that current or voltage into a millivolt level for input to the relays. So That's what they're doing internally. So if we had a sensor that could just use output this millivolt level instead, wouldn't have to. We could do that easily enough with modern technology now. New sensors based on old proven concepts are now being able to apply it in new ways. So these sensors could reduce the wiring costs, reduce the internal components within the relay itself, reduce the weight of the relays, and they could be immune to electromagnetic interference and maybe even greatly improved accuracy on these devices itself. There's three different ways to do this. One is resistance divider for use of voltage measurement. One is Rogowski coils. Another one is outgoing voltage current transformers. So you would have a primary sensor that goes through some kind of data converter in a transmitting system, and then you could send this information to either the protection control or some other area. The resistance divider is just what it says. We have instead of having any kind of a wire wound device, we just have a primary set of resistors. Then we tap the lowest resistor to come up with a secondary voltage. Of course, that's going to be proportional to the lowest resistance divided by the sum of all the resistors in series with each other. This could be used, but it's typically used only on medium voltage applications, and we don't get it to be used on high voltage applications at all. The advantage of this is that it's non-saturable. It's all resistance, so there's nothing that gets saturated. It's completely linear. It's very small in weight. There's no fluorescence or anything. There's no LC circuits to worry about, and it's very, very accurate. The problem to overcome, though, is the resistances tend to drift with temperature and voltage, so that we get some drifting, so that our output may be a bit off under extreme conditions. We have some effects of straight capacitance and the effect of other phases on this also. So we limit it to low voltage applications. Rogowski coil is another method that's being used more often these days. We actually have some Rogowski coils supplied on some of our gas insulated substations. But the Rogowski coil looks quite a bit like it could be a conventional current transformer. We have a primary conductor, and we have a secondary conductor. But the secondary conductor in the normal CT is wound around an iron core. In this case, our secondary conductor is wound around. It's actually an air, or it's wound about some non-insulating type of a material. This could even be on a printed circuit board. And the output of the Rogowski coil is a voltage that happens to be very linear with respect to the current going through the primary conductor. So the VT that we get out of it is some vector times the dIdt of the time varying of the primary conductor current going through the primary conductor. So you could use this either at this voltage level, or you could use this to feed into a data converter, and then go into a process bus into the IED. The first application of this that will be used in our gas insulated substations has just been using an analog value that goes into our relays. The advantages of using a Rogowski coil is that there's a very, very high measurement accuracy, less than 1 to 3% inaccuracy across the very, very large range. You can go from small, very accurate 1 or 2 amps all the way up to the hundreds of thousands of amps, and have it's very linear over the entire range. Wide range of frequencies, typically from a tenth of hertz up to the megahertz region, and it can withstand unlimited short-circuit current because you're never going to get any kind of saturation at all. And it could be physically large or small depending on what kind of application that you're going to have, and it could be applied at any kind of voltage level. So that's the Rogowski hole. The next thing to do is something that's been around for quite some time, optical current transformers. And the optical current transformer relies on a thing called the Faraday effect. And the Faraday effect says that if I have a polarized light, the polarized light will be shifted when exposed to a magnetic field. And the amount of the shift that the light is shifted by is directly proportional to how strong the magnetic field is, i.e. how much current you have flowing through the primary conductor. Our first magnetic optic current transformers were put in back in the mid-80s or so. So what's happened with this is we have a light source, and the light source goes through a polarizer and a modulator, and then the polarized light goes out on a light, or what do you want to call it? Rotator. Through the middle of the rotator, there is a current conductor, and as the current increases in the conductor, this polarized light is shifted, and we measure that shift back at the processor, and we could determine how much current is flowing by the amount of shift of light through this rotator. It's a very simple concept, and when we first put these in for our first applications, we used these, and we had the output of this, of course, is a very, very low level, and we actually put amplifiers on this to feed it into a microprocessor relay that was a 5-amp microprocessor relay, so it had to take a lot of current through our amplifier. So that was, after a while, it was determined that wasn't a very good approach to take. But now with the modern microprocessor relays, we can feed this low level into the microprocessor directly, and it's an analog value, or you can process it and have a numerical value sample value that will go into the relay instead. Here's an application of a fiber optic current sensor at 170 kV applied on a live tank breaker. So in this particular case, we have a SF6 insulation, and on a bushing, we have a fiber that's going up through the bushing to this rotator, and then back down into the sensor electronics. And this is a picture of what this rotator looks like. It's sitting just around this pole of the breaker. So normal current flow is going to be through the breaker. It's going to come through here, through this lower level, then through the breaker, through the contact, then out again. And we can put this rotator or this optical current transformer right around the breaker itself. And you can see a picture of that would be this. It's sitting right over here. It would be sitting right in here. Oops, wrong way. Another way to do it for voltage using the same optical approach would be a voltage transducer. A voltage transducer uses a thing called a Pockell effect. And the Pockell effect is that you have a crystal, and this crystal is affected by the amount of electromagnetic field around it. These fields are made out of this Bi4. This crystal is this I guess I don't know what BGO stands for, which means bismuth germanium oxide or something like that. And this anyhow, so when we put a we put a voltage across this crystal, and the more voltage you put across that, the higher the phase shift across this that goes across this also. So it's similar effect to what we're doing with the optical current transducer, except using a different type of a device but getting the same effect with this shift in the voltage as we change the amount of voltage across at this time. So what's actually happening is that we're shining a light through here, and we're changing the refractive index on the light, so that we see a shift in a phase shift in light as it goes through the crystal. And at phase shift we can measure, and it's proportional to the amount of voltage across it. Here's a picture of a optical metering unit that happens to have a current transducer in it and a voltage transducer in it. So the current transducer is sitting on the top, and the voltage transducer is sitting in the middle of it. And this is used at anywhere from 72 up to 550 kV. And a picture of it that you can see on the station. Here we have mounted from a freestanding, like upside down, on a bus going across in a substation. So this is a optical metering unit that's actually in service right now. Very, very lightweight, very compact, so we can hang them upside down. They're ideal for adding on anywhere in very, very high accuracy class, because they don't have any saturation effects or anything. So lastly, we'll talk about standards. I, being a vice chair of the Power System Reline Committee, tend to push people towards standards whenever people ask me about designs and that kind of thing. And so all of these current transformers, voltage transformers, optical current transformers, and whatnot are all governed by standards that are being written as we speak. The first one being a C93.7 deals with a CCVT, and that's a power line carrier coupling capacitor and coupling capacitor voltage transformer requirements. And it deals with the ratings that you have for standard burdens for coupling capacitor voltage transformers and whatnot. Interestingly enough, there's nothing in the standard that actually talks about CCVT transient requirements at all. That's kind of left to the manufacturers to decide how to set that up themselves, and so we can come up with common definitions about what the transits are going to be, but there's not been any work to, I guess the manufacturers have never been able to get together to determine how to actually define these transients for these applications. Next one is a IEC document. That's IEC 60186. It helps to deal with voltage transformers and for your reference. And we also have the web pages you can go to in order to get that copy. Copies of this presentation will be available for everyone. These PowerPoints, you can get copies of these. Next wing is a C5713 IEEE standard requirements for instrument transformers. This deals with the physical attributes of current and voltage transformers. And then what we get concerned, the one that we refer to lots, is this IEEE C37110 2007, which is a guide for application of current transformers used with protective relaying. This is the guide standard that falls under the jurisdiction of the Power System Relaying Committee, the one that we looked after and update every 5 years. So this is the latest that we have right now. And this one talks about applying a current transformers for relaying. It talks a lot about, from a static and dynamic standpoint. It actually there's a calculator in there that you can use that lets you determine what if the CT that you're using will meet your dynamic rating requirements based on system information and the CT you've chosen and whatnot. You can just input that information in there and it will do a calculation on an Excel spreadsheet for you. So it's very good. I recommend that you get that. The CT saturation calculator is actually on our PSRC website, which happens to be www.pes-psrc.org. And under reports, you'll find that CT calculator in there. And then there's IEC 60044 that refer to different parts of the current transformers and voltage transformers. In conclusion, CCVTs are commonly used for EHV and high voltage relaying applications. Transient response of the current transformer of the voltage CCVT needs to be taken into consideration when you're applying them, and you have some control over the kind of response that you're going to get depending on the amount of how high capacitance CCVT that you buy, the tap voltage that's chosen, and whatnot for these CCVTs. Current transformer application not only needs to be considered from both a static standpoint but also a dynamic standpoint, and you can get the CT performance calculator out of our PSRC website to help in the dynamic considerations for the CT that you're using. The time to saturation of the current transformer is an important criteria in relaying, and specifically it lets you determine if the CT is going to perform adequately for the protection that you're going to use, and hopefully the protective relay that you're using will take that information into account and determining if the CT is saturated or not. Non-conventional instrument transformers are finding their way into the relay business, into relays now, and you'll see more and more of those on the market as they're becoming less and less expensive, and more manufacturers are building these, and the manufacturers of relays who are using these inputs coming into relays. And process bus will soon be here. And process bus is if you have instead of having all of the analog currents and voltages being fed directly into individual relays, a process bus is a method of taking currents and voltages and feeding them through a device out in the system that will digitize that current and voltages and put it onto a process bus and make that information available to all the protective relays. This way you can minimize the amount of copper wire using. You wouldn't be bringing the currents and voltages all the way back to over the secondary wire all the way back into the substation, and so you'll see a lot of that taking place in the future. All based on the IEC 67859-2. You'll see more and more relays that are set up to handle that now. Okay, and in the further final commercial, this webinar was brought to you by the Reliant Product Advanced Protection and Control IEDs from ABB, and what you see here. The next webinar that's going to be held is going to be July 19th, and it's going to be on using a high-speed switch in order to take the place of an uninterruptible power supply. So it's a very interesting seminar. But that will be held July 19th at noon Eastern Time. Then the one following that will be on July 26th on digitizing copper. That will be back at the 2 p.m. time. So that's all for the webinar. If anybody has any questions, or if I didn't answer any questions that you had, just let me know. When shorting CT is good practice to remove conductors from CT secondary. A question came up from Heine. It says, Jeff Heine, that says, when shorting CT is it good practice to remove conductors from the CT secondary terminals? Does it matter if the CT is C or T rated CT? And I guess I'm not quite sure about that question. You don't need to typically I'm thinking you're shorting a CT through some sort of a switch. So if you're shorting the CTL, it's not necessary to remove the conductors from the CT secondary terminals at all. If you're shorting it through a shorting switch, either on the or through a FT switch type that ABB would make. And it doesn't matter if it's C or T rated as far as that's concerned. What causes core saturation in CT? Core saturation occurs in a current transformer, but I guess I started to go through that. But as you put more and more current through the core, the core can only develop so much flux. Each incremental amount of current you put into the CT core, the iron, it develops more and more flux, and it gets to the point where the CT can't generate any more flux, and that core saturates, and that's what causes the saturation to occur. It either causes by putting too much current through it, or by some DC component in the core that helps the flux along. Hope that answers the question. What's the rule of thumb to prevent the saturation of CTs in terms of CT voltage ratings? I guess I don't know. A rule of thumb to prevent saturation of CTs. Again, you'd have to go. It's more complicated problem than just having a rule of thumb. I would refer you to the CT saturation calculator that we have on our PSRZ website, and you can use that information by putting your CT information in there and your system information in there. You can determine if the CT is adequate for your application. Somebody said IEC 60044 is being superseded by IEC 61869 series. Okay, so that's the latest information. I have a lot more information about the ANSI information than I do about IEC stuff. So thank you very much, Roy, for that information. Can we measure phase angle as well using optical CTs? Yeah, there's very, very little phase angle. Yeah, you can measure phase angle using optical CTs if that's what your question is. Now, optical CT, you can measure phase angle, of course, as well, but it doesn't have any inherent phase angle error in it, though. I guess that's what the question was. Thank you, Paul. Can I have a copy of the PowerPoint slides? Yes, PowerPoint slides will be available to everybody. Tracy Noble will give you a link in order to get those PowerPoint slides from this presentation. We are using auxiliary transformer on the secondary side of the main CT. Which one needs to be earthed? Now I gotta using a secondary. Which one has to be grounded? The main one or the auxiliary CT? I guess I'd have to know how these are connected. Are they connected YY for both sides? If so, then you only need to ground the CT1 set to auxiliary. As per rule, CT secondary can be earthed only once in one place. That's correct. You only want to ground it in one place, otherwise you'll get circulating currents and whatnot. Roy, could you elaborate on that question? Let's see. Can you please repeat the website for the current transformer calculation? Yes, the website is called, it's our Power System Reline Committee website, And the website is www.psrc.org. And on that website, there'll be a tab for published reports. And under published reports, you'll be able to scroll down and find the DT saturation calculator on there. So that's what it is. Okay, any other questions? If not, then I got through the whole thing in 90 minutes like Tracy said I wouldn't do. Are you still there, Tracy? Or
of course I'm still here. I can't believe you did it. Great job, Roger.
Sure.
I guess I lost $5. Huh? All right, thank you all for your participation today, and we hope to see you next week. Take care. Bye-bye.